everyone, myself Ankita, faculty of Department of IT, AKGEC. Today I am going to discuss the topic error detection and correction from Unit 2 of Computer Network subject, that is code BCS 603. So I will be discussing introduction, types of error, redundancy, VRC, then LRC, CRC and the checksum. So these are the topics that I am going to cover in this video lecture. Now, when we talk about computer networks, we talk about first OSI layer, and the OSI models have 7 layers, starting from physical layer, data link layer, then we have network layer, transport layer, session layer, presentation layer, and ultimately the application layer. Now, and in the first layer is the physical layer, which is basically handling the raw transmission of bits in the communication medium. Now, next layer is the that is data link layer. Now, what is the purpose of data link layer? First, it in the receiving side, it demarcates the raw stream of bits into frame, whereas in the sender side, what it does, whatever packet it received from the network layer, it encapsulates that into a frame. So framing is one of the main feature of data link layer, and other features include error correction and the control. Now, what does that mean? It means that whatever data that is being delivered, that data should be correct data. And therefore, the purpose of data link layer is to ensure that whatever information, whatever the frame that it is transmitting, and it is received in the same form in the receiving node. So other functions on data link layer is access control, flow control. So today in this video lecture, I will be concentrating on the error control because it's very important. So error detection and correction are essential functions of the data link layer, and it ensures the reliable transmission of data between the devices. Now, whatever data I'm sending from my side, it should be received correctly in the correct form in the receiver side. Now, the data can get corrupted during the transmission. So in the physical layer, when the raw bits are getting transmitted through the communication medium, due to noise or interference, that data might get corrupted, that signals, because what are we doing? We are converting that bits into some signals. Now, if these signals are distorted through the noise or some animation problem, what can happen at the receiving end? So we will not get the correct data. So whenever the shape of the signal is distorted, is corrupted, then we want that it should be known to the receiver that the data is corrupted. So what are the various types of error that we can witness is single bit error. When suppose this is a frame is nothing, is a set of bits. So now this, if I have sent 0 over here, at the receiving side I have received 1. So this is called as single bit error when we are changing only 1 bit. Burst error means that we are changing many bits. So here you can see we are seeing the change in all these 4 bits. So this is known as burst error. So there are 2 types of error that we are going to tackle, and the purpose of data link layer is to ensure that whatever data we are transmitting, it should be transmitted in a way that the receiver is able to recognize that yes, the data has been corrupted. Now, so as to ensure that whatever data that is being transmitted is received correctly, we are adding some redundancy. Now, this redundancy is what does the literal meaning of redundancy means? Extra. So we are adding some extra bits to our message, to our frame, and these extra bits carry some information about the message frame, right? Now, whenever this full frame is reaching the destination, the receiver can verify from this redundant bits, that whether the data frame is correct or not. So you can see we have 2 depictions. One is the sender and other one is the receiver. Now, in the sender, we are encoding. It means we are generating the redundant bits. So we have a message. This message is from the main data frame. Then we are applying some function to it. Okay, that is generator function. We are applying some generator function. That is how we should generate the redundant bits. Basically, generator is nothing, but it is a way it is a method by which we get to know what the redundant bits we should send. So that is generator. And after having, now this generator could be of many types. right? The techniques that we are going to study, that is VRC, LRC, CRC, all these are generated techniques. So we are applying these generated techniques on the message, and the result we get is some redundant bits. And then we are sending this message and those redundant bits to the physical layer, which is then transmitted to the transmission medium. Now, this with unreliable transmission, what will happen? There could be some error that has been included in the message. Now, whenever I receive the information, I will use the checker. This checker will correspond to the generator that we have used in the sender side. And if I get the correct message, after checking I get the correct message, then I will accept that message. Otherwise, I will reject that message. Now, these are the 4 types by which we can check whether there is error in my frame or not. First is your vertical redundancy check, longitudinal, then CRC. This is the most commonly used technique. Now, first we'll look on to VRC, or vertical redundancy check. It is also known as parity check. Now, it is a very simple method. It is the most commonly and least expensive used. It is very least expensive. We also call it as parity check. Now, here we are using redundant bits, which is called as parity bit. Now, parity means, what the literal meaning of parity is the count, right? Here we are trying to find out the count of bits, and based on the count of bits, I am adding a parity bit. Now, at the end, I will be finding out the parity bit. The parity bit is nothing but it depends on the count of bits. Now, take example. There are 2 types of parity, even parity and the odd parity. If in my message, I have even number of 1, okay, the count of even 1 is even, then we call it as even parity. If in my message, the count of 1 is odd, we call it as odd parity. Now, when the data is to be transmitted, the sender will compute the parity of the message. Now, if it is, suppose beforehand only we decide we will follow even parity, right? So, I have a message and I will try to find out number of ones in that, okay. So, if the number of 1 is odd, that is 3 suppose, then I will add the parity bit as 1. So, my number of 1 will be 4. Now, this 4 means I am now transmitting the data which is of even parity, right? Likewise, if I suppose number of ones in my data bit is 4, so I will add only 0, okay. So, in the receiver side, we apply the same rule to check. Now, taking the example, suppose this is my binary data, okay. Now, in binary data, what I will do, I will try to find out the count of 1. The count of 1 is 3. This is out count. Now, I have decided I will, suppose I will go for even parity. Now, what I will do, I will add this 1. Now, the count of 1 in this is 1 to 4. It is now even parity. Now, at the receiving side, when I receive the data, I will check. Yes, if my number of 1 is even, I will say, okay, there is no error. But if the number of 1 received is odd, then we can say there is some error. Okay. Similarly, for the odd parity. Now, see, the problem in this technique is that suppose there is 2 changes. Now, if we have 2 changes, we won't be able to detect the error. For example, suppose I have told this is odd and now this is even parity number, okay. Now, suppose there is a change called 1, 1, 1, 1, 0, 0, 1, 1. Now, see, there is change in 2 bits, right? Now, but still it is even parity, okay. So, what happens? Now, again, I am unable to detect that there is some error. So, the VRC technique will work fine for single bit error, but it does not work in the burst errors. For that, we have LRC technique, that is longitudinal redundancy check. Here, the parity bit is calculated over the column, over a blocks, right? So, we are calculating the same fundamental thing of the VRC, but here we are finding, first we are dividing the message into different blocks and then we are putting it together, and vertically we are finding out the parity bit. Now, it is very simple to implement, and the purpose is to detect the burst errors. So, how it works? First of all, I am arranging the data into rows and columns, and then what I am doing, I am taking my data, divide it into blocks, and then I am arranging these blocks into rows and columns. Then I am calculating the parity of each column. And at the end, in the last row, I will have my parity row, which is now appended with the data. Now here at the end of the receiving side, the receiver recalculate the LRC from the received data. So if the computed LRC matches the received LRC, the data is correct. If they don't match, it means the error has occurred. Okay. Now, for example, take this message. I have this message, and now what I will do, I will divide into 4 blocks. Okay, like this. Then I will arrange them into a column, and then I will find out the parity. How? See, 1, 2, 3. Number of ones is 3, so I will add 1. Number of 1 in this column is 2, so I will add 0. It's even only. Here, number of count is 1, 2, 3. It's odd, so I will add 1. Here, in this column, number of 1 is 2. So, there is no need to add 1, so I will add 0. Here, number of 1 is 3, so I will add 1. So, likewise, I will do for the entire columns and I will get an LRC count. Now, whenever I am transmitting this block, what I will do, I will append this LRC block at the beginning. So, in the receiving side, what will happen? Suppose I have received, I will do the same thing. Okay, I will do the same thing and I will again divide this into blocks like this. 1 1 0 1 1 0 1 0 0 1 1 0 0 1 1 0 1 0 1. So this is what, this is my LRC code and this is my received data. Suppose that. Okay. So I will calculate again. So it is even parity 1 0. Here also even parity. 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 So I have received 0. It means these all are in same parity. That's even parity. So it means there is no error. Suppose there are some changes over here, right? So what I will get 1 1 over here. In such cases, I can deduce that there is some problem in the frame and I will reject the frame, right? Now, another important technique is your cyclic redundancy check. So it is an error detection technique which is used in the digital network. So it is also very commonly used technique in your error detection phase. Now here we are having the data and we are now selecting a generator polynomial. Okay. Now this is a predefined generated polynomial. We are usually keeping them as a prime number. Okay. And it is used as a divisor. Then we follow division of generator polynomial. We are dividing the generating polynomials for them from the message bits. Okay. Now here we are using XOR operation. In spite of difference, finding the difference, I am using the XOR operation. Right. Now, then the remainder, whatever remainder I get after the division process, it is known as your checksum. And at the end, what I will do, whatever checksum, now this checksum is appended with the data bits, right? This is my data and this checksum is appended with data bits. At the receiver side, what I will do, I will again take the message and will divide with the generated polynomial. If my remainder is 0, then it means that message is correct. Right. Now, simple fundamentally, I can say, suppose that this is my data. This is just a representation. Here we are not just representing the as data as a number. Okay. So, suppose this is my data that I have to transmit and this is my generator polynomial. Right. Now, what I will do, I will divide it. 3 2s are 6 and this is my remainder. Now, this is my CRC code. This is my CRC code, this is my data and this is my divisor or generator polynomial. Now, when I am transmitting 7, what I will do, I will append 1. Okay. So, at the receiver side, what I will do, it will add this. Okay. And if there is no error at the, if my remainder is 0, it means that if my remainder is 0, it means that what? That there is no error. Okay. So let's see the example. Suppose I have this data and I have a divisor and I have a CRC. Now this CRC is of n bits. Now if my CRC is of n bits, if I want my CRC code to be n bits, I have to use the divisor of n plus 1 bits. Okay. Now if I have n plus 1 bits as a divisor, I will be appending n bits of zeros to the data before the division. Right? This is my data. I will be dividing with the divisor, and if I need the CRC of n bits, my divisor will be of n plus 1 bits, and I will be appending n zeros at the end of data before dividing it. Now, after following this process, I will receive a CRC of n bits, and this data is appended with the data. At the receiver side, what I will do, CRC plus data, I will divide it, and then if the remainder is 0, I will accept the message, and if the remainder is not 0, I will reject that message. For example, let's take, now I have a message. Alright. So what I will do, I will select a that is generated polynomial or divisor. Okay. That is level. So it will be in the exam, there will be question given. You will be provided with this generated polynomial as well as this message. Now usually the generated polynomial is expressed in the form of x, right? So it could be in the form of like, this is 0, this is 1, this is 2, this is 3. So we can write like this, x cube plus x square, right, plus 1. So this is a generated polynomial which we are depicting in the form of a binary number. Fine. Now what happens? I will be appending n minus 1 0 at the end of message. N is the length of divisors. So my length of divisor over here is n is 4, right? So my CRC will be n minus 1, that is 3. At the end you can see we are receiving 3. So I will be appending how many zeros? 3 zeros. So here I have appended 3 zeros. Now what I will do? I will start dividing. Okay. So you can see 1101 divided by this. Now in the 1 you can see 1101. Now you have to here, in spite of negative dividing, we will use XOR operation. Like see, 1 is same, it means 0. What does XOR means? If both are same, I will get 0. In both case, I will get 0. If it is, I will get 1. This is my rule that I will going to follow. Okay. So 1 1 is 0, 0 0 is 1, 0 1 is 1. Then again I will take down this 0 and I will multiply and I get this. So 0 1 1, 0 0 0, 0 1 1. Okay. Then again I will take down this 0 and 1 1 1 0 1 0 1 is XOR karenge, that's 1 1 0 1 1 like this. Then 0 again. So likewise, when you are continuing this process, at the end my remainder will be 0 0 1. Now you always have to remember that we have to append n minus 1 zeros. If the size of our divisor or generated polynomial is n, so I will have to append n minus 1 zeros. This is mostly the students forgot to add, right? So when we add n minus 1 0, then we perform division operation from the generator polynomial. Now and whenever we are dividing, we are using XOR operation. Okay. Now after XOR, we are at the end, we are getting some value, and that remainder is my CRC code. So I will perform the XOR operation, and at the end, see, I got my remainder as 0 0 1. Now this is my redundant bit. I will be adding this redundant bit to my transmitted data. Okay. So whenever I will get the data at the receiving side, what I will do, suppose this is my data I have received, I will perform the same division. So how will I will do? Like this. And this is my received data. Okay. So I will perform what I will do. 1 1 1 0 1. It is 1 0 0 1 I will take down this 0. Okay. So it will come out to be 0, 1, 1, right? This is 0, this is 0. Again, 0. So likewise, what I will do? 0, 1, 1, 0, 1. So at the end, if I get the remainder as 0, it means data is correct. If it is not 0, it means there is some problem that have occurred in transmission. What I will do? I will reject the frame. Now, very important thing is how we should find out the generator polynomial. Which generator polynomial we should select. So in the divisor is usually 1 bit longer than the desired remainder. So whatever checksum number we want the divisor to be 1 bit more. So if I want my checksum to be of n bits, right? So I will be using divisor of size n plus 1 bits. For example, if my CRC3 means my the CRC code is of 3 bit size, so my divisor will be of 4 bit long. If my CRC is 8, then divisor will be 9 bit long, right? So we have some standard given, which if we don't have a specific requirement, we can use those standard. For example, CRC3 is used for small data where my generator polynomial is of type 11001. Similarly, for CRC8, my generator polynomial is like this. So yes, there are some fixed generator polynomial that we can use. Okay. Now, there are very common use cases that we are used. For example, in ATM and Bluetooth, I use CRC8, whereas in USB and IBM SDLC, we use CRC16, whereas in Ethernet, that whatever LAN we are going through, it is using CRC32. So, another method is your checksum. So, in this method, the sender divides the data into equal size segments. So, what I was doing, we are dividing the data into some segments, right? Now, what I will do, I will divide the data into blocks, and what I will do, then I will add them. Okay, I will add them using the binary addition. Okay, now whatever added sum I got, that is final sum, I will be complementing that, and then I will be transmitting that data along with the checksum value, right? Now, at the receiver side, the received data segments and checksums are added again. If the result is all 1 or 0, it means there is no error. Otherwise, if there's some distortion in the output, we'll get some error. The checksum helps to identify the error, and that may occur during the transmission to ensure the reliable data transmission. Now, let us see. We have a data 1 and this is data 2. Now, this is not different data types. These are just one message. What I have done, I have divided them into different blocks. Now, what I will do, I will add the data words like this. Okay. Now, this is same addition is very simple. 0, 0, normal addition that we do. 0, 0 is 0, 1, 0, 1, 1. And at the end, I get one extra bit. So, what I will do with that extra 1 bit, I will add over here, right? So, I will add this extra carry bit from here to this value, right? Yes, this one is put over here and we add them, right? Now, then I will take the ones complement. Ones complement means I will be inverting the bits. So, what I have done, I have inverted bits. So, it will come out to be 1, 0, 0, 0, 1, 0, 0, 0. This is my inverted bit. Now, and then what I will do, now this is a redundant bit that I have created and it will be added to the data, right? Okay. And then what I will do, I will send it. Now, at the receiver, what I will do, what receiver will do, it will add data 1, data 2 and checksum. If it get all ones, it means there is no error. If there's some changes in the bits, it means there is some error, right? So, in this video lecture, we have discussed various error detection techniques. Now, for error correction, we have Hamming code, right? So, in Hamming code, it helps us to detect the errors as well as it helps to correct the errors. Now, in error detection methods, we have discussed so far about the VRC, the vertical redundancy check, which is called as parity check. Then we have discussed about the longitudinal redundancy check, which is used to detect the burst errors, in which we are dividing the bits into blocks of data, and then what I will doing, we're trying to find out the parity longitudinally from the column wise. Okay. Now then this third technique of CRC, in which we are first choosing a generator polynomial, and then we are dividing the generator polynomial with the data, and then whatever remainder we are getting, we are choosing that as the redundant bits, right? Then at the last, we have discussed checksum technique, in which we are adding the bits and then providing the ones complement of it, right? And after ones complement, we are getting some checksum values, and these checksum values at the receiver added with the data bits, and if the result is all 1, then there is no error detected. So this was all for today. Thank you.